So this year I'm going to be using the David Klein text in my organic chemistry course. And so you may see that my notes sort of follow a similar format to that text. So let's start off by discussing alcohols. First we need to be able to name them. And we simply take off the E of the long chain name and replace that with an "al" for the alcohol. And the OH will take the priority. So that here we would have 1, 2, 3, 4, 5, 6, 7. That's your longest chain, right? And the alcohol will have the 2 position because that's the lowest number for it. So this becomes a 5-methyl 2-heptanol. You can have a double bond still here, and that's still going to be a hexene, but this would still take priority, so that ends up being the number 2 position. This is at a trans position, so this becomes trans 4-hexene 2-al. That's a way to sort of get in 2 different changes at the end of the word. And finally we would have this is an S 2-methyl 3-hexanol. In a ring you still want to make the OH the lowest position, so we sort of assume that it's going to be position number 1. If there was obviously 2 alcohols and it was a diol, then you would need to list the second one. But in this particular case, we would just name that there's a 2-methyl group because the alcohol is considered to be at the first position. So it's 2-methylcyclopentanol, and here alcohol still takes the top priority, but you would move to this side for your numbering so that you get the overall lowest number within your ring. So this becomes 2,2,6 trimethylcyclohexanol. Some common names that you should just commit to memory. This is phenol, and this is benzyl alcohol. As you may recall from general chemistry, OH can hydrogen bond. So alcohols are going to have a higher boiling point and melting point than other molecules of similar mass. You can remove the hydrogen from that oxygen, but it takes a pretty strong base, something like NH2 or a hydride, which we're going to talk about in a minute, which is H-, or something like a metal that doesn't have its charge yet, so it's just basically ready to get rid of electrons, and we'll sort of talk about how that works later. Okay. When considering the acidity or basicity of any type of compound, what you really want to look at, let me put this behind here so you can see the notes more clearly. What you really want to consider is how stable is the conjugate of that molecule. So if you're looking at how acidic something is, you want to see how stable is its conjugate base. Well, we know that this is least acidic and this is most acidic. So let's look at the reason why. There's 2 major things that take place here that can help stabilize a conjugate base. You can have stability happen through inductive effects, so things, it's like pulling a tightrope. So you've got somebody that's pulling electrons from the other side towards it. So if you have an electron mass over here, and you've got something pulling electrons over here, it helps stabilize the electrons that are stuck over here, because basically that means that there's not just one atom over here stuck with all that charge, right? Well, that's what this inductive effect is. So here, all of that negative charge is pretty much stuck on that oxygen. But here we have fluorines that are highly electronegative, and they're pulling electrons back towards him. So that means that this oxygen basically gets some relief from holding on to that negative charge. But sort of the Mac Daddy of stabilizing these things is resonance. Because this isn't actually just like pulling this way. This is actually showing where you can have different arrangements of negative charge that aren't solely on this atom. And so we're going to talk about how to make these later, but if you can see that we can resonate or change where that negative charge is going to be located in multiple ways here, that's the reason why this guy is so much better at taking that negative charge. And therefore, that's why this hydrogen is the easiest to lose. So this hydrogen will be lost most easily because its conjugate base is most stable in holding that negative charge. Good. Now when we're looking at different types of alcohols, we can synthesize them in different ways. We can simply take an alkyl halide and do an SN1 or an SN2 type of reaction to yield an OH. Now be careful, because if you do this with heat involved, you can get an elimination reaction pretty easily. So these can be rather touchy, and you have two different reactions sort of competing there. So we tend to try to do this a different way if we can, but you can do it that way. Okay, so if we start with an alkene, we know that we can do H2SO4 and end up with this guy. Another way to do that is to do through oxymercurization and just do this is mercury, OHC, followed by NaBH4, and you end up with the same type of molecule. This one can rearrange. We're going to look at that later too. So here we can also just do, this is a Markovnikov addition. So you end up with the OH on the most substituted carbon here. On the other hand, if you want an anti-Markovnikov addition and end up with the OH on the other side, you add BH3THF, H2O2, OH minus, and H2O, which you probably should have had in organic 1. Sorry, that's misplaced. Now, to further understand what's going on with alcohols, we have to look at a little bit of what's going on with oxidation states and what that even means. And it's a little bit different term to look at how electrons are distributed. It is not the same thing as a formal charge. So we can determine an oxidation state looking at where electrons are sort of housed in a particular bond. So in this case, all these electrons around that carbon are sort of equally shared because they're all to other carbons, right? And so if we were to split the charge, or who owns whatever electrons are there in a bond, they're sort of split evenly, right? So one goes to this carbon, one goes to this carbon. So if we look at this oxidation state, here's how we figure it out. There are 4 valence electrons on carbon, and right now he has 4 electrons, and so it would just be a net 0 oxidation state. But surprise, surprise, things change when you start to bond to oxygen, hence the term oxidation state. Because oxygen sort of, we say that oxygen sort of owns both of those electrons in that bond. So now carbon only has 3 around it. So that's 4 minus 3. That's a +1 oxidation state. In this case, carbon is going to own, per se, this bond, because a CH bond, we just say that's the way it happens, okay? Oxygen, on the other hand, is going to own all of the electrons here. So we say that this carbon has these 2, this carbon has this 1, and oxygen has all of those. So 4 minus 3 is +1. But on a carboxylic acid, a carbon would only have to split those between another carbon here. This oxygen takes all those electrons, this oxygen takes those electrons, so we have 4 minus 1, that's a +3 oxidation state. So in other words, you can get to a much different oxidation state just based on what you're bound to. Here's the long and short of it, guys. If you have more bonds to oxygen, it's going to be a higher oxidation state. Or your molecule is more oxidized. That just makes sense, right? If you have fewer bonds to oxygen, then that means that you've got a lower oxidation state, or it's more reduced. That's what those terms mean, okay? So now let's look at what a reducing agent is then. So what a reducing agent should do is it should give you more bonds to hydrogen, or fewer bonds to oxygen, right? And an oxidating agent should give you more bonds to oxygen. These are reducing agents. These are the 2 most common. So let's think about this. This is basically a metalloid. This is a metal. Both of them right now have a negative charge to them, even though I did not draw that in right there. Because H minus is not going to float in the middle of anything that you could actually measure, right? So this is actually sort of housing your H minus for you. So this is what's going to be a hydride. This is sodium borohydride. This is lithium aluminum hydride. And they're basically housing this guy right here, because that's what's going to come flying off as soon as it can. Well, it makes sense that this would want to be expelled from this guy, either of these, because basically you've got a negative charge on a metalloid and a metal. And so once that happens, wow, BH3 is a lot more stable, isn't it? And aluminum doesn't want this negative charge, so it wants to get rid of that pretty quickly. So basically these guys are getting rid of H minus. They're very reactive, and this is more reactive than this one, which also makes sense because remember, things with metallic character want to have more of a positive charge to them, and so this is more desperate to get rid of that negative charge than this one is. Okay? So let's look at this in practice. Side note, palladium on carbon will still react with a C-double-O bond to give you an OH. Now, remember, it still works with this guy too. Okay? But when we're dealing with these hydrides, they do not touch a double bond. You can either use NaBH4 and ETOH, or you can use lithium aluminum hydride and followed by water. Two separate steps, okay, to end up with this OH. They're just not going to react with this double bond because an H minus is going to attack the carbon down here that's partially positive, and therefore it doesn't have anything that's partially charged in this bond and cannot react with it. Okay, there's no charge differential there. So lithium aluminum hydride will also work with esters and carboxylic acids. Yes, and will give you this OH. Yes, that is correct. Okay, good. Make sure you count your carbons. 1, 2, 3. 1, 2, 3. Don't forget this guy, okay? Because I've seen that happen very, very often. This will come off in this particular reaction. So there we go. That's our first lesson.